Good evening to you all, colleagues and distinguished guests, and welcome to the 2024 Stewart Memorial Lecture, and a special welcome to Mr. Callum Stewart. It's my first honour to introduce Steve Roberts from Martin Baker, who will open the lecture this evening. Steve.
Good evening, ladies and gentlemen. Welcome to what I believe is the 53rd Stewart Lecture. We've only had a dropout, I think, in 2020, and we did the 2021 virtually. So I think this is the 53rd, which is awesome, and thank you again for great attendance. Now, the Martin Baker connection with the Institute of Aviation Medicine really goes back to 1945, when you had an irascible Irish engineer having to take into account aeromedical opinion on ejection. So there was a relationship that started in 1945, really with the then Wing Commander Bill Stewart, who became the Air Vice Marshal running IAM as we knew it. And again, importantly, that didn't stay there as the Wing Commander got promoted and all the way through the ranks. But again, as he moved on, he was invited back in August 1945, when ejection seats were really at their infancy, and Martin Baker was really playing with the only aeromedical information really from the German research, and that research still exists in the Bundesmuseum in Munich. But the Wing Commander was actually fired up the 65-foot tower. So for those who know, we're based near Junction 16, the M25. We built a 65-foot rig, and the Wing Commander, Bill Stewart, was invited to actually test what was then becoming the face blind. So again, ejections were over the head, and the face blind was to position the back, and he was one of the guinea pigs from what became the Physiology Department, or Physiology Lab, of 1945. And then later, in about 1962, his follow-on was Wing Commander Peter Howard, who also actually did an ejection test from the Meteor. So again, the connection with IM goes into today. So again, it's quite right and proper that we introduce the Stewart Lecture. Ma'am.
This year, I would also like to warmly welcome Andrea, wife of Squadron Leader Paul Goodwin. Many of you will know Paul, who was the training officer of RAF CAM's Aviation Medicine Training Wing from 2014 to 2024, before his untimely death too soon earlier this year from motor neuron disease. With his characteristic RAF regiment humour, Paul was indeed the life and soul of the training wing. He carried out his role as training officer with the same passion and commitment that had seen him succeed as an RAF regiment gunner. Paul loved looking after the King's College London Aviation Medicine Diploma course students while they were at RAF Henlow, and all of the students knew who Paul was. His efficiency, command of organisation, and simple enthusiasm really shone. As the training officer, Paul was instrumental in defining the pathway to attain DSAT accreditation for RAF CAM courses, but more importantly, he will be remembered for his warmth, his friendship, his grinning smile, and his jovial spirit. He loved Champagne Tuesdays and parties in the officers' mess. Earlier this year, the Centre of Aerospace Medicine was honoured to receive an aviation art print of an underwater aircraft presented by Andrea. This artwork, which also reflects Paul's passion for diving, now hangs in what was Lecture Room 1, but is now called the Squadron Leader Paul Goodwin Theatre. On behalf of the Stewart Memorial Trust and all here this evening, it is my privilege to welcome Andrea to this evening's lecture. It's the perfect occasion to recognise Paul's commitment and his exceptional service to aerospace medicine. Andrea, as a mark of the loyalty and the friendship that Paul showed to many others, we extend that friendship now to you, and we welcome you into the close family of aerospace medicine experts and enthusiasts. Before we do hear this year's lecture, I would like to congratulate this year's Stewart Award for Cadets and Stewart's Prize winner. This award is open to UAS medical students and cadets who are invited to submit a piece of work either on aviation or space medicine. And this year, the panel of judges enjoyed reading 4 different submissions. However, it was some new research that was conducted by Flying Officer Karis Sung that won the panel's judgment. Caris currently works at JHG North. Her study of research was on the relationship between action video game players, aircrew recruitment, and sustainability due to enhanced cognition. And I will leave you to chat to Caris to find out what that research told her. We've already heard from Steve, thank you, about the Stewart Memorial Trust Lecture, and it's my delight to invite Wing Commander Bonnie Posselt, who will lecture to us this evening. It's tradition that we hold the lecture here at the Royal Aeronautical Society, and I understand that Bonnie is going to talk to us about helmet-mounted displays, and I will leave it there. Bonnie, over to you.
Thank you, Anne. Hello, good evening, everyone. Hopefully you can hear me, and my mic is turned on, because I absolutely need some microphone help this evening. Hopefully I'm going to get through the next hour. So if I could have my slides. And I just want to say, I was sat where you are now back in 2010 as a junior doctor, fascinated with all things aerospace medicine. Really unbelievable to be stood here today. It really is an absolute privilege to be talking to you, so thank you very much for the invitation. I did put some slides together, I do promise you. It's going to be a long hour with me trying to do some display work. Yeah. No video, just the slides. Welcome to, there we go. Hurrah, the slides exist. So I'm going to be talking to you this evening about helmet-mounted displays in aviation, how they've evolved over time, how they've become a critical part of our military operations. Part of my PhD topic was investigating human performance using helmet-mounted displays over in the US in the Operational-Based Vision Assessment Lab at Wright-Patterson, and hopefully I'll be bringing some of those lessons to this evening's lecture. So standard disclosure slide, but I do specifically want to point out credit to BAE Systems, Thales, Kinetic, Collins Aerospace for providing me with some of the images this evening. Otherwise it would have been a very dull presentation without any pictures. So we're going to talk about what is a helmet-mounted display, why are they even useful in aviation, how they've evolved over time with the changes in technology. We'll spend a little bit of time looking at the limitations of a helmet-mounted display, and then at the end of it, we'll just talk about what is the possibility for the future. So confusingly, an HMD can stand for either a head-mounted display or a helmet-mounted display. However, ultimately, it is a compact optical system that is attached to the head, be it in a helmet or otherwise, and it's used to project digital data to the user. And I'll point out at this point, I'm not going to be talking about night vision goggles, because night vision goggles are actually image intensifiers where you directly view the scene. What I'm talking about is something that's digitally created and then transmitted to the eye. And it's a spectrum. You can have a basic, simple, monochrome type display, like these glasses here, that display something like the time or a checklist. There's no link to the outside world. Of course, here you have a much more complex system that is individually fitted. It is full color, wide field of view, and has a head tracker. These complex systems are able to accurately locate the orientation and the position of the head, and they're able to do so under high G and with dynamic, fast, quick head movements. There's 5 basic methods for head tracker. You have optical system, infrared, you have inertial, you have electromagnetic, you have acoustic, and you have hybrid. Hybrid type head trackers use 1 or 2 of those different methods to improve the accuracy and reduce the latency of your head movement, like when you move your head, making sure that the data tracks appropriately. So why do we use an HMD anyway? Well, primarily the most important reason for using a helmet-mounted display is it enables you to keep your head out of the cockpit. And this is particularly important when you're in a very visually demanding environment. So you can imagine if you're flying in formation, looking at another aircraft that you're very close to, or if you're refueling mid-air, trying to get your probe into the drogue. If you're doing a battle fighting maneuver, you don't want to take your eye off the enemy. If you're taxiing on the ground and looking out as to where you're going, or if you're flying low level, close to the ground. Any of these situations, the time taken to move your head back into the cockpit, look down, look at your flight reference systems, and then look back out. That's time taken. And a lot can happen in that time if you're traveling at Mach 1. So, it's a flight safety issue if you're not keeping your head out of the cockpit. So that's one of the benefits for being able to look at the information with your head out. Secondly, and arguably most profoundly, is that HMDs have the ability to vastly improve your situational awareness. When paired with a sensor, an infrared, thermal, or a visual sensor, you're able to accurately recreate the outside environment virtually inside your helmet-mounted display. And this is particularly important in a low, what we call a degraded visual environment, a DVE. So when you're flying at night or you're flying in cloud and you can't see the outside world, well, now you have a sensor that can do that for you. And this was a simulation study that was performed using an HMD. And they actually showed that wearing an HMD improved your waypoint, your tracking performance, and your landing accuracy by 300 to 400%. And incredibly, improved your target identification by 12,000%. So yeah, statistically significant. And this is an example from the Elbert X-Sight system. So it's taking an infrared image, putting it in your helmet mount display, and then also putting terrain mapping over the top of it and route guidance. So you've got arrows pointing you to where you need to go. And thirdly, you can link your head-mounted display, or you can link your head movement to a weapon system, so to a gun or to a missile. And what that does is it means that you can look somewhere and then you can identify your target and you can fire your weapon or your gun. And instead of having to move the whole aircraft round to point at your target, you can now simply look and shoot your target. And why that is beneficial is because it reduces the physiological demand to the pilot. So instead of having to pull G to turn the corner, instead press a button and let the missile do the 50G turn to go and get to the target. So it reduces the reaction time, and ultimately it's a force multiplier. So hopefully I've managed to convince you that helmet-mounted displays are a good idea. So let's talk about the different types of display that you can get. So there's different systems. So on the left here, you have a monocular system. That is presenting one image to one eye. And these are the lightest systems. They're the simplest, and they're the least expensive. However, they have a number of human factor issues, particularly binocular rivalry. When you show your eyes two very, very different images, your brain has a real trouble trying to mix them together. So you end up just suppressing one image. So you don't even attend to it. You can't even perceive it. So that's a real issue. Also, the mass on your head is asymmetric, so that can contribute to musculoskeletal injuries. In the middle, you have a biocular system. That's where you present the same image to each eye. A majority of systems are this biocular setup. So you eliminate the problem of binocular rivalry with this system. But it's only with the binocular system, here on the right, that you're able to present stereoscopic depth. So it's a slightly different image presented to each eye, which is how we view the real world. And it's with this system that you can see 3D or real depth. Binocular and binocular systems obviously are much heavier because you've got two optical systems, and they're the most complex to engineer and difficult to maintain. But the mass, at least, is you want to make sure it's symmetrical across the helmet. So breaking it down even further, so you've got the type of display, and then this is what you display within your HMD. So first of all, you have information that can be screen referenced. So over here, this is simple information that will stay in your vision, no matter where you're looking. Wherever your head is, you'll see that information. And that can be simple stuff like your fuel status, your speed, and your height. You then have a platform referenced information, and this is stuff like a forward HUD. So it only becomes visible when you're looking forward, and then when you look to the side, it disappears. And then you have geo-referenced information that is tracked to the real world, so something like terrain mapping. And of course, you can have a mixture of all three types of information within the one display. So HMDs have evolved significantly over time. We've gone from your Mark I naked eyeball all the way to these complex biocular and binocular systems that are critical to the aircraft. And in some instances, you can't even fly the aircraft without the helmet-mounted display. You can't just swap it out for another one. And so we're going to look at that this evening. So this is the first kind of HMD as such. So 1915, this is the Integrated Helmet-Mounted Aiming and Weapon Delivery System in Pratt's helmet. And you have a gun mounted within the helmet. There. Okay. And so wherever the pilot is, wherever the soldier looks, the gun is unconsciously aimed to wherever it is that they've looked at their target. And the soldier then is able to bite down on this tube to fire the gun to get to their target. And the same look and shoot philosophy is embedded in HMDs today. Interestingly, this is actually a dual-use helmet. The crown part of this doubles as a cooking pan, with the barrel acting as the handle for the pan. And the spike in the top is not for fighting, is actually to put your cooking pan, shove it into the ground to support in-field dining. So we now skip along quite a few years. The next real thing to talk about is in the 1970s. And the reason why there's such a big gap between 1915 and 1970 is simply the technology didn't exist. So in 1970, we see the Visual Target Acquisition System. And this is a fixed reticle that is flipped down over the pilot's eyes, and it provides a collimated light. And by collimated, I mean that the light is parallel that you're seeing, so it's at optical infinity, and it would light up and tell you when your target is in range. But it didn't get into operational service because there's a few technology limitations with it at the time. Outside of the US, we have this Russian system, the Schnell 3UM on the MiG-29, that when paired with a missile was actually highly effective in the 1980s during the Cold War. So to counter this Russian superiority at the time, there was a real surge in HMD development in the early 1990s. And here we have the display and sight helmet system, the DASH system. It takes a while for this to warm up, so I'm just going to walk and point. And you can see it's actually embedded in the helmet, but it's quite a big, bulky helmet. Sorry, I couldn't find a better resolution picture. And this is really when we start to see the criticality of HMDs. So it was just a target acquisition system, but when paired with the Python 4 missile, it became a force multiplier and is your real must-have for your fourth-generation fighter. And this sets the scene for the Jehemics, which we'll talk about in a few slides' time. And just to show you, this is a slightly different system. This system is a visor projection system, so that is to say your optics are in the helmet. The display then bounces the image off of your visor and into the eye. This is a monocular system giving you a 20-degree field of view display. Here is a slightly different system where you have the screen, the transparent screen, monocular down in front of your eyes. And this is the Scorpion HMCS that is operational today. So what was the UK doing during this time? This is the Alpha helmet. As you can see here, we've got a little probe that you're able to just rotate down, and that sits here, and it then bounces the image off of this part of the visor and into the eye. And what the pilot would see is an LED. You've got 9 different arrows that can tell you where the target is, so point you towards cue you towards the target. And then we move on to BAE Systems developing their first binocular system, which is the Viper series of helmet-mounted displays. And this is, CRT is cathode ray tube based. And for this system, we now have sensor imagery. So for the Phantom aircraft, they had a sensor located on the front of the aircraft that was then able to project imagery into the helmet-mounted display. And because of the technology of having a beam splitter mirror at the top, you can see it in the brow of the helmet there, they're able to display symbology on top of a sensor-generated image. And you can see here doing some flight trials where the test pilot has the cover over their helmet-mounted display. There is a safety pilot in the aircraft as well, but they are using this to test to see if they can recover from unusual attitudes based on the sensor-generated image projected into their visor. And this is the predecessor for the Striker helmet-mounted display system. And then, this is something I very much learnt during this presentation, is we also tried experimentally within oxygen mask system display. So they mounted a display onto the oxygen mask to see if they can take some of the mass off of the head. Unfortunately, it didn't last because under G, the mask just moves too much and the display would just completely disappear from your view. But a nice type of HMD that I didn't know about beforehand. So now we move on to a system that I'm sure most of you have already heard about. So this is a joint project by the US Air Force and Navy. And this really is the game changer in HMDs. The Joint Helmet Mounted Cueing System, or JHEMIX as it's most commonly known. It's a monocular system, visor projected, giving you a 20-degree field of view. And the key point is it's platform agnostic. So all of the optics are in this top bit here that you can clip onto whatever helmet it is that you want to integrate it with. And it was used in, I saw some crazy statistics up to like 90% of the fast jet fleet at one point in time around the world. So it's used in many different countries and many different platforms. The issue with having your optics all the way up here, obviously, is your center of gravity and all your mass is right up here. The rotary world is also embracing helmet-mounted displays. So 1969 was the first documented HMD that I could find in rotary platforms. And this is the SPH-4 Cobra attack helicopter, where you have a monocular reticle that, again, is slave to a mechanical gun in the back. So the pilot can look wherever they look, they can then operate their gun. And then the 1980s, the Integrated Helmet and Display Sighting System, or IHADS, as it's commonly referred to. And we haven't really updated much since then because we still use it in our Apache aircraft today. And you can see it's a monocular system. Unfortunately, the thing about this system is it's fixed to your right eye. There's no left eye option. So for 40% of the general population who are left eye dominant, it's much trickier to work, and it has a lot of issues with binocular suppression, binocular instability, up to there's all sorts of varying statistics, but like 60–70% of pilots say that they have issues with it, particularly at the start. And another, and just to point out, it's quite bulky as well. You can see here, it's really impacting this aviator's peripheral vision on the right-hand side, so it's obscuring part of their peripheral vision, which is not ideal. And then this is a prism clip-on monocle that can be used for rotary wing operations as well. There are also binocular versions for this. So the Top Owl is the binocular version for rotary wing. Full binocular overlap, 40-degree field of view. And it's integrated night sensors. So the two blue circles on either side of the helmet, that's your night vision camera. And that can then display the night vision generated image into your HMD. Biggest issue with these is that the two tubes are more than 4 times the width of your normal eyes. So you have hyperstereopsis, where you get the impression that the world is much further apart than it really is, and it can induce quite a few visual illusions that are quite hard to overcome. And the MyDash modular integrated display system is a similar type of version for rotary wing. The two cameras on the side giving you a binocular HMD image in the middle. And of course today on current platforms we have the F-35 helmet, and this is pretty much the only helmet that we have in the UK that you cannot fly the aircraft without. You have to be wearing the helmet. It is a full binocular overlap. However, they only use it in a biocular form currently for a number of different reasons. And you've got the night vision camera right in the middle up there, so you haven't got that issue of the two separated wider than your eyes. And the one thing I like this picture for, because it illustrates your exit pupil. So this is you have the optics at the top, bouncing the image off your visor and directly into your eyes. Now your eye has to be within that green circle in order to be able to see the information being projected. So the helmet has to be accurately aligned to the individual. And the reason why you say, well, why don't you just make the green circle wider so it's easier to keep it in the middle? Well, that's extra mass of an optical system, that's extra power. So you want to minimize the size of the exit pupil, but keeping it aligned to the individual. Of course, we also have the Striker series of helmets. The Striker 1 is worn in Typhoons today, and we are moving towards the Striker 2 helmet. Again, full color binocular system, has high accuracy head trackers. And I'm delighted to say that this evening we have a Striker 2 helmet upstairs. Many thanks to Stuart Penny from BAE Systems who's brought that along. So I encourage you all to go and have a look in a helmet mounted display and see how you find it. But we've got that tonight. And of course, they're also used in simulation to recreate the mission environment in trying to make it more realistic and also reduce costs of versus flying. And you can see there's some pretty crazy, wacky big designs out there. They don't have to go through the rigors of high G and vibration as an operational HMD would have to do. And you can use these, the head-mounted displays as well. So we're going to spend a bit of time talking about issues with helmet-mounted displays. And it's key to point out at this point, just because you can have a helmet display that is full color, massive field of view, binocular, you don't necessarily, do you need it? Because you don't want to deal with all of these issues if you don't need to use the HMD in the first place. So the need for the HMD and what you need it to do is paramount. Attention tunneling. So you don't want your HMD to be so encompassing to draw you in, to be so realistic that you actually don't attend to the outside world. You're still flying an aircraft. You still need to maintain that situational awareness and that airmanship. All the things that are red, we're going to talk about in a little bit more depth in following slides, so I'm not going to spend too much time on them now. Sensor location, we've spoken about it already. If the information that you're capturing is remote from where your head is, then you're going to get a different perspective of it, and that's going to give you some optical illusions. Motion sickness, absolutely. If you turn your head and it takes a little while for that information to catch up with you, that's going to give you spatial disorientation and likely motion sickness. So you need to keep those latency rates down as low as possible. Obviously, that costs. Latency and slew rate we've just spoken about, and of course cost. So your average F-35 helmet's going to cost you about $400,000, so they're not cheap. Misalignment. So when you have two well-aligned images in a biocular form, your performance is about 10 to 20% better when it's well aligned. If you get some misalignment between the two optics, this is what you're going to see, optical misalignment. And you can see it's a little bit uncomfortable. However, your performance is not going to be worse than monocular. So two eyes are always better than one. And it does depend on the individual. We all sat here, if we were to close our eyes, have a degree of ocular misalignment, or ocular imbalance, I should say. You have a number of muscles that keep your eyes in place, and when you're rested, they tend to drift slightly. So when you're asleep, you have your eyes aren't looking straight all the time. When you're awake and you're focusing on something, you use those eye muscles to focus in, and you are able to tolerate a degree of misalignment. However, those people who have a greater muscle imbalance or phoria are going to find that harder, because they're going to have to work harder to force their eyes to fuse the two images. And also, it's not just phoria, it's also length of time spent doing that. So if you can fuse an image, you can do that for, you know, a minute, but if you ask me to do that for 12 hours, it's going to be really hard work. So misalignment causes eye strain, nausea, headache, and double vision. And while we normally are able to fuse horizontally misaligned images pretty well, because our eyes can do that really easily, vertical misalignment is poorly tolerated universally. So if you have a degree of vertical misalignment, regardless of what you do, most people are going to see double images. And distortion is a part of this. So distortion can cause optical misalignment. This is a map of your visor. So we spoke about quite a few of these systems rely on bouncing the image off of the visor to then project it into your eye. So if your visor was completely flat without any distortions, this map would be all the same color. However, that's impossible. So you get a degree of distortion in different areas of the visor, and that can induce misalignment. If a pilot drops their helmet and dings their visor, that can misalign the visor. If you cycle the helmet through hot and cold temperatures, you get expansion and a retraction of the materials within the visor, and that can also cause a degree of misalignment. And that's something that we're working on at the moment to try and characterize what that is. Because at the moment, your helmet comes out from the line with a set, tolerable alignment issue, and then that's it. It's never checked after that. So there's currently some work undergoing to try and measure misalignment within helmets to see if there are any issues with it today. And again, you have to contend with the prism of a canopy as well. And a canopy that's thicker in some parts and thinner in other parts is again going to affect your perception of the outside world and the imagery. So I spoke about optical misalignment. There are two types of misalignment, and they get confused very easily. Optical and misalignment is when you get that double image because the two optics aren't properly aligned. And this is misalignment with the outside world. So if your geo-reference data doesn't fit what the real world is saying, that's called misalignment with the outside world. And this has caused issues. So this is a mishap that occurred in 2020. A pilot, F-35 pilot, was flying at night, so a DVE, a degraded visual environment, and this is what they should have seen in their HMD, the runway, artificial horizon. And unfortunately, there was a misalignment, and this is what they actually saw. So they ended up with a really steep landing, and they came in too hard, and they stoofed the aircraft into the ground and wrote off an aircraft. They survived, but thanks to an ejection seat. Green glow. So this is something that is an issue with F-35 helmets in particular, but if your display is a liquid crystal display, you're unable to turn the pixels off, and you get some bleed through of the light. And you can go from flying in day to if you're flying at night, all of these pixels are off, but it's going to scatter the green light and give you this haze that's really difficult to see through. So you then end up turning the HMD off, right? But then you don't get the symbology, which is the benefits to why you need it. And this is important for helmets going forward, as we're going to move away from fixed HUDs to everything being in your HMD. You don't want the pilot turning your HMD off if it's the critical part of your flight. The fix to this is to upgrade it with organic LEDs, and that is something that's being done with our helmets. The human vision system, so I'm going to spend a little bit of time on this, because this is where the mainstay of my research was. So for a given helmet-mounted display, you've got to think about the user. And every single person in this room and in the pilot community has a different level of visual acuity, stereopsis, which is your binocular vision, contrast sensitivity, color discrimination, ocular alignment, accommodation, fusion range, vergence accommodation, decoupling, and visual pathology. When I talk about vergence, accommodation, decoupling, I just want to explain that. So vergence, moving your eyes, and accommodating, focusing your eyes, are linked together. So when you have a binocular display that's displaying stereo depth, those two things get decoupled because your focal range is always your focal range. You can't change that. But if you're displaying imagery in depth, your vergence, you're going to have to change your vergence. So it can be quite hard to decouple those two things. For those of us who are a little bit presbyopic or require reading glasses in older age, we're not as bothered by it because we do have decoupling of our vergence accommodation, which is why you can't focus on anything, but you can move your eyes here. So actually, for older folks, this is less of an issue, but for young folks, they find it really uncomfortable to decouple their vergence and accommodation. So, what should the visual standards be for each one of these things, and how do we reliably test them? And hopefully you'll be able to appreciate that we've come quite a long way from the naked eye to now using these visually demanding systems, but guess what? Our standards haven't changed that much. So part of the work of CAM is to try and relook at our test methods and be able to provide evidence to inform the standards, not just transparency, as I think was mentioned earlier, but the fact that they're evidence-based standards, not just because that's how they always were. So we want tests that are repeatable, where they're reliable and give you good data that you can trust. What you don't want is a test like this, okay? And so this is hung outside a flight surgeon's office in America. And again, everyone's going to pass it, but and it's important to point this out because if you've got a helmet-mounted display that is operating in colour, in stereoscopic depth, and it's going to cost $10 million to train that individual to get to that point, what you don't want is the fact that they cheated on their test 10 years ago and they actually can't see in colour, they don't have depth perception, and their visual acuity is pretty terrible. But hey, they passed their tests. So this is an area of work that we're looking into. And I'm just going to talk about stereopsis in a little bit of detail. So stereopsis is the ability to perceive depth based on the slight difference in image on the right and left retina that occurs because there is a difference in perception between each eye. Binocular disparity, then, is the angular lock between each of the images, and stereoacuity is the smallest angular difference that you can be measured between those two different images. So if you're focusing on point F, you will be able to perceive that A is closer towards you without looking at it, okay? And that will be a single image. B will be, it's too far out of your fusion range, so it will appear double. But you do this every day, but you don't really realize it until you start thinking about it. But up to 30% of the general population have deficient stereo vision. You're not born with it, you develop it over time. But you don't need stereo vision to go about your activities of daily living. People cope just fine. They use monocular cues such as obscuration, relative size, motion parallax. And the same is true for aviation. You can fly with one eye, with monovision. However, your depth perception is likely to be altered, and there has been studies shown that people who lack stereo depth normally crash their cars more and sometimes can have steeper landings. So in the military, we do test for it, and we want our aviators to have stereo vision. However, if you're using stereo in a display, you now no longer have monocular cues. You've got to be able to perceive the stereoscopic depth. And why would you want to use a binocular stereoscopic display? Well, it could be that it helps declutter information. So you've got a screen of information, but if you put something important out in depth, you're going to see it a little bit more. It improves search time, efficiently capture attention, and can reduce your cognitive workload. My personal research showed that by displaying a warning symbol in stereo depth didn't improve performance. However, I strongly believe that there are other applications of stereo depth that will improve performance. But I did show that those with the worst stereoacuity, so I made sure I measured stereoacuity in all of my users, is that those with the worst stereoacuity did find it harder, quite a lot harder, and that was shown in our measures. So up to 30% of people don't have stereopsis or poor stereopsis, so you need to make sure we've got a good test to make sure we identify it. Integration. So when you're thinking about helmet-mounted display, it's important to think of the whole system. We spoke earlier about a 2 kilogram helmet, roundabout. If you've got a 2 kilogram helmet at 1G, if you're under 9G, you know, it's going to be nearly 20 kilograms sat on your head. So you have to really try and keep the mass down as much as possible. We saw that a little bit on the videos from Martin Baker earlier, that when you eject, you know, your whole head is going forward as well. So you want to reduce the mass as much as possible, keeping your center of gravity well aligned. You need to be able to accommodate eyeglasses. Not everyone can deal with contact lenses or have corneal refractive surgery. So you can see this aviator here has their glasses on. And what does that mean for progressive lenses as well, which is something that we've just allowed into the fast jet community. And I think there's a bit of work to be done there. It needs to be able to integrate with all of your life support systems. So your mask, you don't want your mask leaning on the visor, distorting the visor further. It needs to interact with you can see there's quite a bulky stole. So, you know, you've got that at the back. You might have ponytails or thicker hair as well. So the fit of the helmet needs to be impeccable. You need to cover a full anthro range of your users. You need to have a data connection to the aircraft. So this is one of the issues with the F-35 helmet, is this thick optical cable that when you're moving your head around dynamically, that needs to be sturdy. And you don't want it to snag on anything, and you don't want it to limit or restrict your head movement, but you don't want it too long either. You want unobstructed dynamic head movements, thinking about the canopy structure and the canopy itself. You don't want to banging your head into the canopy. And it needs to perform under G and with vibration. It needs to work seamlessly with the crew escape system. And also when you're in the outside environment, exposed to 600 knots of wind speed, wind blast, it needs to be able to be safe then as well. It needs to be durable, and the maintenance schedule needs to be supported with it. So one of the issues with the F-35 helmet, like I said, is you can't fly the aircraft without it, and it's individually fitted. So that means that if a pilot's having an issue with it, are they going to report it, and it takes weeks and months for it to go off to the factory and come back? No. So they're going to fly with it, and it's been the theme of the day, I feel. So we need to bring the support and the maintenance closer to the pilot so we can fix these things, so then they're more likely to report them, so they're not having to fly with a misaligned image and just putting up with it because they don't want to be grounded because they can't fly their aircraft without it. And the future. We are going to be asking more of HMDs. Hopefully I've convinced you that they're a good idea, but we're going to be asking more of them in the future. We are going to be asking for greater luminance. We're going to be asking for better resolution, wider field of view, full colour, and so they're here to stay. It may be that we move away from the everything in one helmet system to a more modular system. So if you're flying around for 95% of the time at day, do you need to carry your night vision camera or sensor on your head, adding to the mass? Not necessarily. So we're looking into, there are teams out there looking into how best to, where should you put the camera? Obviously it needs to be close to where your eyes are, because we've spoken about remote sensor location. But is there a modular way of having it? Visor technology, I think this is something that we're going to see in the future. Currently you have two visors. You've got a clear visor and then you have a tinted visor. But it may be that we can use photochromatic or electrovoltage visors in the future that are able to switch between the two, darkness and clear. The reason why they don't exist at the moment is because the time delay from going from dark to clear is just not quite down there yet, so that's why they've not been used. And optical technology is improving. So these are waveguides. So these are lenses that use total internal reflection, and they are able to provide you a high luminance, wide field of view, like big exit pupil in a compact form. So the way that they work is that light gets beamed down to them, and then within the glass substrate, it's bounced, weaved all the way through the glass and then out in an exit pupil towards your eye. And these really are pretty cool. But they are really complex to engineer, and they're quite costly, so they're not routinely used at the moment. Eye tracking. So it could be with inbuilt eye tracking to helmet-mounted displays that they're getting to the accuracy levels that you may be able to just depending on where you're foveating, depending on where you're looking, you can provide the best resolution to minimize your power and constraints. So you have your resolution just where you're foveating. It could also be, there are some studies going on at the moment linking performance flying your aircraft with saccade and eye movement. And so, is that something that we should be looking at for our selection metrics? At the moment, we don't even look at contrast sensitivity, peripheral motion, and maybe it's something that we need to be looking at. Deployability, I've mentioned. These systems need to be deployable. It's all well and good them working in the lab, but do they work out in the middle of nowhere? And we're going to be wearing them for much longer duration sorties. So they need to be comfortable, both from a musculoskeletal point of view, but also from an ocular point of view. You don't want to be fatiguing the eyeballs. And just to tell you that this is RAeS 6. This is a clip-on type HMD that's being investigated at the moment and trialed. And you can clip it on and it will display adversary aircraft for you to train against, so you can track. And that's something that at CAM we're involved in. And I'd like to talk about this graph. We talk about colour. Is colour the best? Well, colour is good for lots of things, and it does give you a very profound sense of, you can identify things much easily with the use of colour in someone who's able to appreciate the differences in colour. But I want to just have a look at this graph. Colour, you've got to be careful about the use of colour. First, you have to make sure that the colours are separated enough that you're not going to get confused between red and amber. And careful about what colours that you use. So on this graph, on the y-axis is symbology visibility, and on the x-axis is how bright the outside world is. And for the same luminance, you've got lines of each different colour. So as the outside world gets brighter, it's going to be harder to see symbols universally. Red, green, yellow, magenta, cyan, and white, all you can see pretty well, but uniformly, blue is very difficult to see. So be careful about using blue in helmet-mounted displays. And of course, not just aviation, but looking to space. And you can use, not currently used at the moment, but you could use HMDs in a spacesuit. So this type of display is screen reference, so it's skull fixed to the head, and it's just giving you some very simple data like the length of the EVA, and your physiological data. Unfortunately, the artist who's drawn this obviously didn't get the memo about not using blue. So hopefully this won't actually get into production. But yeah. So that's me. Hopefully these are my references. I recommend, if you're interested in this textbook is available freely online at helmet-mounted displays, issued by USAREL, and that's a good reference. And yeah, happy to take any questions or talk more about this in more depth afterwards. And please do go and see the Striker 2 demonstration upstairs and have a look at it. And look at the different colours and try opening and closing each eye. So you've got a biocular form, so you can see an image in each eye, but you'll only see one image with your, as long as you don't have a whopping great four and you can't fuse the images. But anyway, so thank you very much for your attention, and have a good evening. My voice made it. Yes, just about.
I'd like to now invite Mr. Callum Stewart to present the traditional glassware to Bonnie for her lecture that she's just presented.
Bonnie, that was an absolutely fabulous lecture.
Thank you.
So interesting and so well presented. Don't you agree, everyone? Yeah. Thank you very much indeed, and it's a pleasure, absolute pleasure to give you this.
Thank you very much. Thank you very much.